So in the element approach for flexibility matrix method, we have so far discussed about a continuous beam example, a plain truss example, and a portal frame example. But in all those examples, we did not have any support settlement. Now this section describes about the effect of support settlement when you go for the analysis with element approach or structure approach in flexibility matrix method. So this is the effect of support settlement in flexibility matrix method. To illustrate that, I have taken the same example discussed in the previous session where there is no load over here. The same portal frame, same dimensions, 10 meters, 4i as the moment of inertia, 10 meters span, 4i the moment of inertia, 5 meters the span of this, and I the moment of inertia. The support settlement is given as this. Theta d, that is rotation at this support, is 0.002 radians clockwise. Delta d, this support moves down by a distance of 0.015 meter downwards. So because of say maybe soil movement below that, this support has rotated as well as it has settled down by some distance. So what is the moment produced and what is the shear force due to these support settlements in the structure is the question over here. Right. Now as before, to develop the structure coordinates, to develop the structure flexibility matrix, we require only the geometry part of it, geometry as well as other properties like I and E. Once you have that, you can develop the structure flexibility matrix through element approach or system or structure approach. And we have obtained already the structure flexibility matrix. When these are the structure coordinates, when we remove this support, this will become statically determinate. So if you assume 1, 2, 3 as the structure coordinates, we have delta equal to 1 by 6a into 750, 375 minus 150, 375, 2000 minus 225 minus 150 minus 225 and 60 symmetric matrix. That is the structure flexibility matrix. Now these are the element coordinates, of course, in an element approach. That is only for completeness of this solution. Yeah, the equation which is to be solved here is essentially delta L plus delta into R is equal to delta. Delta L contains the displacements corresponding to structure coordinates due to the externally applied forces in the release structure. Delta, of course, structure flexibility matrix. R contains the redundant forces or the unknown forces corresponding to the structure coordinates which are unknowns in the system. And delta, this vector contains the applied displacements corresponding to the structure coordinates, or they are the support settlement values. Now if you write the equation full, because there is no external forces in this structure, we have delta L containing zeros, 3 zeros corresponding to 1, 2 and 3 coordinates. This delta 1 by 6 EI, 750, 375 minus 150, 375, 2000 minus 225 minus 150 minus 225 and 60 into R1, R2, R3 is equal to delta, the displacements corresponding to these coordinates. Along direction 1, we have no displacement given here. Let us put 0 there. Corresponding to direction 2, vertical direction at D, we have delta D is equal to 0.015 but downwards. So you put a minus sign there, minus 0.015. Rotation, clockwise rotation here is given as 0.002. So they are the elements of the delta. Now, wherever a support settlement or rotation is specified, we have to assume a coordinate over there. That is the most important thing over here. And fortunately here, we have support settlement given corresponding to support D. A settlement of 0.015 and a rotation of 0.002. They are accommodated in this particular equation like that. Now, you can solve this equation for R1, R2, R3 by inversion of this matrix or by solution of three simultaneous equations. Well, if you do that, we are going to get R1, R2, R3 as 5.27 minus 2.259 20.706. Now we can substitute this in this place and find out. You draw the bending moment diagram. You can draw the free body diagram of this piece, and this piece, and finally we can make a bending moment diagram. The diagram may look like .64 here. Connect them. This is 5.64. The moment here is 16.96. Say that much. Here is 69.66. That is the BMP. So we have a point of contraflexure at this point and at this point. So in the previous sections, we have been discussing about the flexibility matrix method. Essentially, we are solving an equation like this: delta L plus delta R is equal to delta. This one. And we have replaced delta R with delta into capital R, where R contains the unknown forces corresponding to the structure coordinates, and the structure coordinates are equal in number to the degree of static indeterminacy. Delta L contains the displacements corresponding to structure coordinates in a release structure due to externally applied forces, and delta is the displacements due to support settlement, or the final displacements which are given, which are available in the structure. So this is the compatibility equation which is solved in case of a flexibility matrix method. We have seen two different approaches for establishing the structure flexibility matrix and the delta L vector. We have seen that the second approach, or the element approach, is much more systematic than the first approach. In any case, initially, after removing the unknown forces equal to degree of static indeterminacy, we are making a release structure, and we find out the displacements corresponding to the structure coordinates due to the externally applied forces in that. and then we find out the redundant forces or the unknown forces by solving the compatibility condition. Once you get the redundant forces, you can find out the other forces through calculation by using the equations of equilibrium, and we can draw, if you require, we can draw the bending moment diagram, we can find the shear forces in case of rigid jointed structures like that. In case of pin jointed frames, say plain trusses or even space trusses, we can find out the axial forces in all the members. So that is the matrix approach, which is a convenient way of doing analyzing the structures when the degree of static indeterminacy is lesser than the degree of kinematic indeterminacy. But we can see that the degree of static indeterminacy of frames, rigid jointed frames, when you go to the higher end, when you go for a multi-shielded building frame, ds will be much higher than the degrees of freedom or degree of kinematic indeterminacy. In such cases, it is better to go for a displacement based method, which is going to be discussed next. First, the slope depression method, and further the stiffness matrix method. Now, we can also notice over here that there are different choices for the identification of the redundant forces. In this case, once you find the value of ds, we have several choices for the redundant forces. This is only one choice over here. We can also have the moment here, the moment here, and the moment here as the unknown forces. There are other choices too. Likewise, in case of any structure, even in case of a plain truss problem, you can find different choices for the redundance. Whereas, when you go for a displacement based analysis, the displacements or the degrees of freedom are almost fixed at the joints. So there may be a unique choice. There will be a unique choice of the unknown displacements in case of a displacement based method, whereas there are several choices for the forces in case of a force based method. So that is an account of comparison of the methods, and to appreciate what is going to be discussed further as the displacement methods, I have given this account. In the coming sessions, we are going to see the displacement based methods, slope depression method first, and then the stiffness matrix method. First of all, we will see the structure approach, and then we will see the element approach in that, and further we will discuss about the direct stiffness method. Okay, so we will close this session with this.